Good evening, everybody. My name is Don Murphy. I'm a board member at the Science Institute, and it's my great pleasure to introduce tonight's speaker. But first of all, I'd like to acknowledge that we're on the territory of the Tanquachon Council and the Kwanlin-Dun First Nation, whose people lived here for thousands of years, and they're our friends and neighbors, and it's just great that they have done that so that we all can join them up here. Tonight's lecture is being presented by the Yukon Science Institute. The Yukon Science Institute is a nonprofit organization that seeks to promote public awareness in science activities in the Yukon and to aid and facilitate scientific research and development. As part of our mandate, YSI coordinates the lecture series that this lecture is a part of. And before I introduce our speaker, just a reminder that 2018-19 memberships will be available at the membership table. Many of you have already gone there, and we've taken in quite a haul tonight. It's a bit confusing, but we are updating people as they come in. Please join. We really appreciate the support, and with it you'll receive emails about upcoming lectures, which include, on January 27th, Eric Sprott will be speaking on paleo horses, and Daphne Buxbaum will be talking about what dogs know and how they know it on February 17th. The Yukon Science Institute is funded by the Yukon Department of Tourism and Culture, Heritage Branch, and supported by the Yukon Beringia Interpretive Center, both ventures that are highly funded by our generous taxpayers to the south of us, and I hope we all appreciate that. Tonight, our speaker is Benoit Turcotte, and he's going to be delivering a lecture on rivers and streams in winter, the love-hate relationship of water and ice. Benoit completed an undergraduate degree in civil engineering at Polytechnique Montréal in 2004, a master's degree in hydrotechnical engineering at UBC in 2008, and a doctorate in river ice engineering at Laval University in 2013. He was a research engineer for 5 years, working on many aspects of cold regions watersheds, including flood forecasting, flood mapping, and flood proofing, before joining Yukon government last summer. And Benoit is the hire that happened after the retirement and ultimate death of Rick Janowitz, so he's filling some big shoes there. Benoit has a real passion for small streams and large rivers and considers himself a hybrid hydrologist, engineer, geomorphologist. And he arrived with his wife and 3 kids, few months ago, I guess. 6 months ago. So please join me in giving Benoit a warm White House welcome to Whitehorse. Ugh.
Low. Good? Yeah? Not too loud? Okay. So I'll turn off a few lights. No, that's on. Okay. That's this. Okay, so theater, so no one sees me anymore. I'm here. You see me? Yeah? Okay, so thank you so much for being here. It's good to be here tonight. It's my first time at this museum, and like Don said, I've been here for 6 months, so not a lot. You read probably the title of that presentation, and the love-hate relationship of water and ice. So I thought about that a week ago, and then I released this title. And then I thought, well, how am I going to do that now? You know, like putting some emotions into river ice. Just give it a sec. I'll just make sure that this does not make too much noise. Okay, I shouldn't be moving. Okay, so I decided to start with this picture. So this is the first form of ice that you can see in any drainage system, in any watershed at the beginning of winter. We call it spray ice anyway. So it's basically just drops of water that freeze on cold surfaces. And what's interesting about this type of ice is you notice that the ice is not in contact with the water. So from a love-hate relationship point of view, it is as if you have like two people standing on each side of the dance floor, and they're looking at each other, and should we start a little relationship, a little dance? But they're still shy, so they don't touch each other yet. And then something happens when the ice and the water reach, and then they touch. But usually that happens when the water temperature drops at 0 degrees Celsius. And that's basically a good symbol of that. You can ask me later, how did that form? It's quite special anyways. It's a complicated setting to create that form of ice. And then, once they touched and they start dancing, they know each other, it creates very beautiful ice. And you can see water flowing on top of ice on top of water, and then the dance starts. The relationship really starts. So that's, again, ice forming in steep and small streams. I should use this here. Oh yeah, exactly. Okay. And then this is a photo from a helicopter, a river back in Quebec, and you can see the nice pattern. Each rock on the bed of that channel has an ice shell, and there you really see the relationship between water and ice. So ice is slowly extending on the ice surface. Sometimes it builds up at the bottom, and then it creates just beautiful shapes. So you can feel the love. You can feel a relationship there. And so that introduces my topic. So I'll present first, I guess, a little theory about river ice for those who are not too familiar with it. Then the chronological part of the presentation is freeze up, midwinter, and breakup, so from the fall to spring. Then I'll introduce some complexity to that. We'll talk about Yukon challenges and some concluding remarks. So let's jump into the theory here. So Yukon River, I just love this place. It's gorgeous. So let's start with two parameters that we don't really control: geology and climate. This is really well, climate we do actually control slightly, but hopefully we wouldn't. But then the watershed and climate are really like two parameters that are, they just happen to be there. And then the open water part of this river diagram is that the geology influences here, oh, look at that, channel morphology and channel dimensions, whereas climate conditions through snow, rain, really influence the hydrological regime. Now, if you want to create some ice, you need first to talk about the thermal regime. So the thermal regime is basically the water temperature in your creek and your river. It's influenced by the geology, through the channel dimensions, through friction, through groundwater heat, and by climate conditions as well, of course. And then the way, because I used to be this river ice engineer, I thought that ice was so important that it would stand right in the middle of it, right? And it fits well, actually, because you see that ice processes are affected and affect the thermal regime. They're affected and they affect the hydrological regime. They are affected by climate conditions. In certain extent, for very large lakes, they could actually influence local climate, but let's take that apart. And Ice processes also influence the channel dimensions through erosion, abrasion, sediment transport. So ice processes really stand in the middle here. And you can see that there's a lot of double arrows, and I do mean it. Like there's really a relationship between that. And so ice processes do affect the channel morphology. And the channel morphology indirectly will affect the thermal budget and the ice processes and the hydrological regime and so on. So there's really like a huge connectivity between those parameters. Now, in terms of space, let's see that you're in the headwater region of a watershed. This waterfall will generate an ice cover that is unique. It's unique because of its morphology. It's a waterfall. But the shape of the ice that forms every year could be actually different. Well, from year to year, it could be actually different, depending on climate parameters as well. Then if you go downstream, in rapids like this river, you'll find different types of river ice, different processes, different timing in terms of freeze up, break up, and then down to a larger channel like the Yukon River, lower gradient, also distinct river ice cover, distinct hydrological processes, and so on. So you really have a continuum from upstream to downstream. So in terms of space, so that's what's happening. Now, in terms of time, well, usually we're here in Yukon, so would say that the ice cover starts forming in early November, more or less. So you have open water October and June, and then in between you have freeze up here, you have midwinter, and you have breakup. And these could be actually quite quick. Freeze up could be very rapid and dynamic, and so does breakup. It could be sudden. You have an ice cover, the next day you have no ice. So it could be actually like in a matter of day before you actually get to no ice. And then in the spring, it could take also one evening, one night, to go from open water to complete ice cover. And then, for some other rivers, it could be more gradual. Freeze up could extend over a month, maybe more, at a specific location or at even more at the watershed scale. And the breakup could also be quite gradual. So the ice could melt in place, like, for example, in lakes. But this presentation really focuses on rivers. So now, number two, so let's dance. Let's talk about freeze up. So the way I'm presenting this, first with this background picture showing stationary ice on the side of the river and ice drifting at the water surface, which is called frazzle. So frazzle starts forming in the water. Well, it's just a matter of the water wants to freeze, so it generates ice, but the ice is just like floating. It cannot settle anywhere. So it's part of the flow, right? What's really important here from this hydraulic point of view is really the stationary ice. That's the ice that has an impact on water velocity and water depth. So introducing here five parameters. So the air temperature, the discharge or flow, water temperature, stationary ice, and water depth. So we'll go from early freeze up to almost a midwinter. So the first cold spell, so it happened here in Whitehorse, I would say the real first cold spell maybe early November this year. And the runoff was declining. Sorry, I heard something? No comment? No? Okay, maybe I'm wrong on the... Yeah, exactly, and I'll get to that. Yeah, exactly. So it hasn't been cold. Yeah, I'll get to that. So the flow is declining. Okay, why the flow is declining at the beginning of winter? It's simply because it hasn't been raining for a while. So the discharge of all the rivers in the drainage systems all across Yukon, cold regions, it's declining. Then you reach a point where the water has lost enough heat so that its temperature reaches 0 degrees Celsius, 0.00. Then, as soon as you get that, you have stationary ice in contact with the ice cover. If you don't have a water temperature at 0 degrees Celsius, you don't have stationary ice. And if you have stationary ice, you don't get water at a temperature above 0 degrees Celsius. That's just the way it is. And then when you have stationary ice that forms, then this represents an obstacle to the water. So it cannot flow as quickly as before. It has an additional obstacle. It's stationary ice. So it slows down. And because it slows down, the water level rises. And why the water level rises is simply a matter of continuity. You have a given amount of water that goes down your river. And then if the water velocity slows down, then as a continuity, water level has to rise. This generates a decline in the discharge downstream because you have ice and water that does not flow downstream. So now you have a flow decline, and as a result, the water level, which is locally higher, it drops downstream. So you get this phenomenon of destabilizing the drainage system. Now, what we've seen this year so far 4 times, mild weather. So mild weather will create a slight melt. If ice melts, then the obstacle melts, and then water level rises because there's water and ice added to the flow. So then you have this answer. And then if the water level rises downstream, it breaks the ice. The ice just formed. So it's just floating at the water surface, and if the water surface happens to rise, then some ice will break. It will add to the flow again, and you'll have additional flow, and therefore an additional rise in the downstream water level. And then you go back to cold. And then you have formation, the water level drops downstream, and then it just goes around. Now it's our 4th, I believe, here in Whitehorse, our 4th mild period since the beginning of winter. So it went 4 times around this loop, and eventually goes back to, it goes to midwinter conditions, a complete stable ice cover. And when the cover is complete, the blockage is complete, there's new equilibrium in the flowing conditions, and as a result, all this up and down tends to attenuate, and that's the beginning of winter. So that frees up from this complicated diagram, and I spent enough time on it. So let's see now this graph. So on this graph, you have the date, 26th of October, 7th of December. So it's actually now. This is happening now. It's the Yukon River below Pelly, the Pelly River. And you have the relative water depth here, relative because it's arbitrary datum, and the air temperature here. Don't be scared with the -60. We don't get -60s yet. So just to let you know that the first part of the graph here, what's happening? You see like this water temperature rising, you know, it sends pulses. It sends pulses to the system. But what's happening with this water level? It's quite stable. Nothing's happening. But then, once you get to a water temperature of 0 degrees Celsius, which is the red line, then things start dancing. Water level, discharge, upstream, downstream, ice formation, and you can clearly see a first cold spell at the beginning of November, then mild, cold, mild, cold, and then we're back to mild anyways. And this is dancing. Look at that. It's really like you can see up and down, and these are probably discharge variations on a daily basis. And then this huge peak here. This is a combination of ice melting and ice drifting downstream and hitting an obstacle and forming a jam and then releasing and so on. So basically you have a backwater effect here of 3 meters. So that's decent. It means that the ice that's drifting and it blocks, and then the water level rises because all the water cannot flow easily, and you have 3 meter backwater, and then it drops, and then it starts back. And of course we're not yet close to midwinter. I heard that even the Porcupine River at Old Crow is not frozen. Most rivers are not frozen across Yukon right now, so it's special, but that's life, anyways. So it really shows that once the water temperature reaches 0 degrees Celsius, that's when all the system comes alive. That's when you have this relationship that begins. And then you also have different ice processes that will generate different signatures. You have gradual processes such as thermal formation of surface ice. These are just crystals that migrate on the river. Border ice is the same thing. It could be also recruiting some frazzle from the flow and then progressing. The coverage progresses towards the middle of the channel. I'll show a picture of that. And these are gradual processes. These are thermal processes, and as a result, changes are so slow that the impact is slow. So you'll have instabilities that are actually not of large amplitude, and they extend on a long period, as opposed to dynamic processes such as the freeze-up congestion and jamming, or anchor ice. And this is very dynamic, and as a result, you'll have a lot of pulses in the system. You'll have water level that goes up and down, and so on. So let me show you some pictures of that. So thermal processes. So this is thermal ice. It's actually quite special ice. It's ice that is not really touching the water, and it's progressing so slowly that there's not a lot of flow that contributes to the formation of ice. And as a result, this very fragile ice manages to extend on the entire stream just because there's no variation in water level. So it's actually a good relationship. It's very fragile. If the discharge increases, everything breaks and all the ice is flushed downstream. Border ice, so you see here on this river, so this river is flowing in this direction here, and it's about 50 meter wide. And so you have frazzle slush drifting, and when it rubs against the bank, the border ice here, right here, that white line, then sometimes when it's cold, it will actually, a few ice crystal will stick. So progressively this channel will close. Again, it does not really generate a lot of water level variations. Now, on the more dynamic side, let me try this video. Hopefully that works. Oh, I see something. You see me? Where is it? Oh. Okay. So, yes. Okay. So on this video, what you'll see is actually a freeze-up jam. You'll see it's a time lapse, and here you go. So it's jamming, and then it's opening, and then it's jamming again. And then you see the water level right here. It's actually going up and down and up and down. So let me just play that back because it's so fast. It's so fast. Whoa, 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 whoa. Sorry about that. Play again. And just pay attention to, so this channel is open. There's some slush, and then pay attention to the water level right on the side. And you see how dynamic this thing is. Okay? And then even after it's complete, look at that. It's a complete ice cover, but it's still going up and down. You can still see some water. And this thing is breathing. Every day it's breathing, and it's going up and down for several weeks. And why is that? It's simply because at that section, the ice cover is complete, but upstream it's not complete yet. So it's sending these pulses downstream, and you have some instabilities. And it's really, it keeps on dancing, really. And then this graph actually shows what you've just seen. So this is a water level relative. This is just 1 meter in elevation, just to give you a sense. January 2nd to January 7th. Hopefully we don't get to this in Yukon soon. That's freeze up in Quebec, happening right after Christmas on a specific year, on a specific river. So what you see is kilometer 15, 14, and 12 to the outlets. So you're actually going from upstream to downstream. And what you see first is this is stable, no ice, and then this is freeze-up jamming. And then you see this thing dancing. It's dancing. And then 24 hours after, it freezes up 2 kilometers upstream, and this thing dances. And then 1 kilometer upstream, 24 hours after, it goes up. And so that's the freeze-up jam that moves from downstream to upstream. Okay? And in the meantime, well, what's interesting is that little peak here. That little peak is jamming and release. And it creates this wave here, and it creates this wave here. So this wave is traveling downstream. So you can really see the little peak, that the little pulses, how this whole system is dancing, right? Now, how do, one more thing about this is eventually this thing gets flat and gets flat. The reason why is that there's rapids above that, and rapids have a different regime, okay? So they cannot freeze like that. And this video shows actually how rapids can freeze in winter. It's a time-lapse video again. It's a bit slow. It's slower anyways. We had here a water level logger, so we could capture all of it. So we could really understand what was going on. So it's a small stream, but the same happened on larger rivers. Let me find this. There you go. So you'll see night and day. Fortunately, we had a moon. So you can see how ice builds up from the bottom, and then every night and every morning, it builds up. You have a snowstorm, doesn't matter. It keeps on rising, rising, and rising. Okay? And that's a lot of water. That's a lot of water and ice stored. Where's the stream? You cannot see the stream anymore. And then mild temperature arrive, and you have this collapse of the ice cover. So what happened here is that the water level was rising, 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 and then with mild temperature, all the water was released. So this system actually sent a huge amount of water downstream, and it could potentially generate some breakup. So again, all the system is alive, and there's a really complex relationship between water and ice here. So I'll show it again, just to show you that. So in this type of stream, there's no frazzle slush. Every ice that's formed in the water actually sticks to the bed or sticks to existing ice. And that's why you have really transparent water, no frazzle, and you have these ice dams that tend to form. And that's how you usually form an ice cover in fast-flowing water. And the collapse of that, the collapse is typical of more southern regions, but it's also happening here. And because it collapsed, then the water is still exposed to cold air. And once you get cold air again, this process starts again. So you'll go up and down and up and down. It will send a lot of instabilities downstream. Now, just a word about the discharge depression. So we're saying that at freeze-up in large systems, there's a lot of water stored in tributaries and the main channel. So this is the Yukon River. Estimated discharge here, the blue, and the gray is the temperature. And this is 2005 Water Survey of Canada. Thank you for this data set. And this is October 2nd to the end of the year. And what you see here is temperature that goes down and then up and down, so really unstable. But then look at this discharge, how it's dropping, and then suddenly it goes from 1,000 to 600. And then it remains very low until it meets back with this dashed line. So that's the discharge depression in the Yukon River at freeze-up. That's typical. It's estimated. We cannot really confirm the amount of water. Here, the area under the curve is actually 600 million cubic meters. Now, if you take 600 million cubic meters and you divide by the area of all the rivers in all the drainage system upstream of that location, you'll find out that maybe all the rivers and streams, that their water level rose by about 0.5 meter to 1 meter. So that's actually the amount of water that does not flow at freeze up and that will be added to the flow at breakup. So that's a good illustration of discharge depression. Now, I think it's last slide for the freeze up. What are the consequences of temperature instabilities as we see right now? Late fall runoff, if it's high, if it's low, and gradient morphology. Is the morphology homogeneous, or is it really varying? And the answer to that is they all have a role to play in the duration of freeze up, in the dynamics of freeze up, and in the amount of water and ice that's produced, the amount of ice that's produced in the system. The more instabilities you have, the more ice will be produced. And right now we're seeing a lot of mild temperatures and then cold and then mild and then cold. So my role here at the Yukon government is to forecast breakup. And I'm becoming nervous because from my point of view, rivers now are producing more ice than they usually do because they remain open. There's still no ice cover right now. So there's still room for more ice production that will accumulate at specific locations, forming ice jams and all that. And then I'm starting to be nervous, right? So just I'll keep that in mind anyways at breakup that we had a weird freeze up this year. And freeze up processes and patterns may appear chaotic and unpredictable, so we like to say that. You see the signals going up and down, but each little peak and each little drop finds its logic somewhere in the drainage system. There's a reason for each of those, but it's really complicated to actually track that. Now, midwinter, a few slides about that. I call this harmony. So there's the dancing. Two people meet, they start dancing, and then let's say that they get married and there's harmony. And why is there harmony? Well, the rivers are insulated. So water, what's the role of the ice cover here? Well, the ice cover is protecting the water against freezing because it's an insulating layer. So water can keep flowing because there's an ice cover. And the ice cover is there because water is there. So it's harmony and it's stable. There's low ice production rate. It slowly thickens, but very gradually. And hydrological conditions are stable. So that's a typical subarctic, Arctic scenario. Now, is there a possibility of having instabilities in winter? Yes. And if you have midwinter thaws, like we see a lot in the south, tell me about how many breakup events in winter I've seen in Quebec City over the 9 years that I was there. I would see probably one every year with major ice jamming and floods and all that. And this is moving. With climate change, this is moving north. So it's to keep in mind as well. Heat sources such as lakes and groundwater feeding into rivers and streams. So if you have open water in winter, it will melt the ice downstream when it's mild, and it will produce more ice when it's cold. And so the system will keep sending little pulses. So every time you see open water in the winter, it means that the system is still alive. It's still moving, dancing. Waterfalls and large rapids that can barely freeze, same logic. Hydro production, sometimes we need electricity in winter, right? And so we open more turbines, there's more flow in the river, and the river, you know, the flow is stable, and suddenly it rises, so it creates breakup and all that. So as an hydro producer, anywhere in Canada, in cold regions, we have to be careful about that. And the last word is Aufweis. I think there's some German people in the room. Aufweis, it's supposed to be from German ice on top. Not sure if I'm right. Anyways, you can ask a question or make a comment after the presentation. It's usually what it's believed. And then Aufweis is a special form of ice. it really forms in shallow streams, in wide rivers like the ones you've seen along Klueni, St. Elias Mountains. Really wide rivers, very shallow. These rivers tend to freeze to the bed, and then when there's more water that flows from mountain sides and from the ground, this water starts flowing on top of the ice. So now it's really not harmony, because this water is exposed to cold air and it freezes, and then more water comes on top and it freezes. So it can create these huge icebergs in the middle of nowhere. And then you get there in the middle of summer like that. That's in the Tombstone Park last summer. And you have like 2 meters of ice in the middle of nowhere. What's that? Well, that's elf ice. And it will melt slowly throughout the summer. So that's definitely a type of ice that really creates instabilities all winter long. Now a word about breakup. The most dynamic period of the year. I call that divorce. Sorry, but winter ends anyways. And so at one point, the ice and water have to separate, right? And this is from a plane. You can actually see the little tire here. This is Dawson City, right at breakup last spring. I was actually with Rick Janowitz at that time. And yeah, we just missed breakup in town, but we clearly saw the big ice run, all the ice from upstream reaches going down the Yukon River. Of course, here you have the ice, you have water, you have snowmelt, but you have all the discharge depression, the water that was stored at freeze up. It's now part of that. And it's so strong that it traveled more than 200 kilometers in 24 hours. Okay, and that's unusual. Usually breakup would stall, form an ice jam, and then stay there for a few hours and then release. But this really kept on going towards the United States, towards Alaska, and on the following day it was way downstream. We can see it. So this was a really interesting breakup. I'm not sure it's typical of the Yukon River. Usually I think it stalls, but we've heard of breakup progressing really quickly downstream under specific conditions. At that point, it was, I think, 20 or 25 degrees Celsius in Dawson. So a lot of snow melting and a lot of water entering the channels. Now, how to explain breakup quite simply. So why is this background picture? This is just a big chunk of ice standing on the side of a river. You can actually see that quite a lot in the spring. And you can see it's still really transparent, so this water, this ice is still strong. It's still strong as opposed to an ice that degrades. We'll have a picture of that. Then that's a graph. And this shows forces against time. So it's a conceptual graph anyway, there's no numbers. You have a resisting force, so that's the ice cover. Let's say that you have 1 meter of ice, and it requires really a lot of pressure, a lot of push, and a lot of pulling on this ice cover to break it. Fortunately, as the sun gets stronger and as air temperature gets warmer, the ice will start to melt and to degrade. More degrading than melting, actually. You won't see the ice just melting in place in rivers. It melts, the cover melts slightly, but it loses its integrity. And that's why it's becoming weaker over time. And then you have the driving force. The driving force is the gradient of the river, and more importantly, the flow. So that's the flow that's pulling on the ice cover, that's pushing on the ice, and that's creating breakup. And when these two lines meet, that's when the ice cover at one location is mobilized, lifted, and carried downstream. And of course, downstream, the ice cover could be weaker or stronger. So you'll have maybe some jamming going on. And when breakup happens at very low forces, or really late in the spring, we call that a thermal breakup. When it's early, or when the forces are still strong, that's called a dynamic or mechanical breakup. You can imagine that dynamic and mechanical means more potential for ice jamming and flooding. So that's one of the rare videos that I have showing a complete thermal breakup in a stream. Okay, so it's a time-lapse video, and what you see basically is that all the ice will melt in place. It snows, it snows. You'll see a fox at one point there, fox watching breakup right there. Oh, went fast anyways. And then you see all these ice islands. They're actually melting, and there's no ice run. There's no ice coming from upstream. It's really gradual. Then the discharge increases because there's snow melting, and then you're back in, well, spring or late spring, summer conditions. So this is really thermal because the ice just melted in place, and it really requires special conditions to create that. This is typical of a thermal breakup. These are ice candles. That's how people call them, and that's how scientists call them as well. Ice candles, they're about the length of, the length of a candle is actually the thickness of the layer of ice cover. Could be 20 centimeters long, for example, and they all detach. It's a degraded cover. You can see it on the banks of the river after breakup, and you can just grab the ice and grab a bunch of candles. So each candle is about 1 or 2 centimeters thick and about here 15, 20 centimeters long. Now, the most interesting, because it has the most impact, mechanical breakup. The first reach to break generate pulses. So the ice breaks in one reach, it jams. So it forms, it stores water, there's less water downstream, and then the system starts dancing again. And if it's not sequential from upstream to downstream, that's when you have important ice jamming events. And so I'll show a video after of that for those who haven't seen an ice run. But let me start with this graph again. The water depth, relative water depth, and this is 24 hours. It's on a river close to Quebec City. And if I start upstream here, the water level is rising slightly, and then boom, it rises here. That's an ice jam. And then there's a little wave, and there's a little release, and then more ice come, and then the ice jam gets larger. It generates a higher backwater. And then here it releases. And when it releases, it generates this wave 2 kilometers downstream, and again 2 kilometers downstream where it generates an ice jam. And then you have another wave here with ice. You can see it here. And then it brings more ice, and the jam increases. So you see how measuring the water level at 3 locations really tells you the history of that system. It's dancing, but it's dominated by ice jams in this case. And so this big wave here is actually, so you can see a bunch of waves in the system. This is the video. It was a 17-minute video, but you know, we don't have 17 minutes. So let me try that. It's about 1 minute, maybe, or 30 seconds. It just shows you the strength. So this isn't a small river in Quebec. Okay, you can imagine if the Yukon River is angry, and it wants to break up really quickly when the ice is still strong. You can imagine the amount of the strength of the ice and the power of that event. So here it generated an ice jam of 2 meters. It flooded a guy. The guy was happy. He was watching baseball. He said, "I'm happy. I'm okay." Anyways, it was fun. And then, so this is 2 meters. Here in Yukon, at Dawson City and in Old Crow, the backwater of ice jams can reach 6, 7 meters. Okay, so it's even more significant. But you can see the power. You can see some trees are crushed here, and so it's a very powerful event. And yeah, this is probably the most dynamic phenomenon that one can see along a river in cold regions. Now, some divorces are happy, some are rough. Let's say that a thermal divorce, a thermal breakup is more happy because there's some collaboration. And when it's really mechanical, it generates consequences, right? Like a rough divorce breaks a bridge. That's East Southern Quebec in '94, huge breakup event. Dawson City, 1944, sorry. Angry rough divorce, rough results. It just happens that there are kids on this photo. Sorry about the link with the divorce. It's just ice and water. It's nothing to do with the kids. Kids are happy. You can see that they're happy. I just thought of that now anyways. Now, topic number 5. So how complex can that be? So I feel that what I've been telling you so far is complex, but it can be more complex anyways. This is an example of complexity. How can this ice form? It's basically, it requires a small channel. It requires a rain event late in the winter, and then cold, mild, cold, mild, cold, mild. And every time it's mild, the water level settles, and then it allows an ice cover to form. And then when it's cold, it's forming this, the discharge decreases, and so on. So you have 3 different signatures of temperatures and specific morphology here. So I've presented a video of that. It's ice formation in rapids. What's interesting is that usually the ice will form on rocks, and then it will merge and then create these ice dams. But I was just interested in that when I was there. What's going on? This seems to be just there, but it's actually not moving. And taking an aquatic picture, it's actually just anchor ice that happened to accumulate there, and as it reaches the water surface, it forms this plate. So it's really something unexpected, and it's fragile, but if there's no breakup, it will form this ice cover and will contribute in closing the surface of this river. And yeah, so you can see an aquatic picture. So when you're a fish, you hate that. You hate that because it's cold. And when you're a fish, usually you want to find shelter between rocks. But then, when you're under this thing, you cannot breathe, there's no oxygen, and it's cold. So anyway, so fish don't like that really, so they tend to find shelter where water is a bit warmer. And yeah, just to let you know, so this ice piece, this ice plate, we actually took it and we sent it. So this picture is actually a CAT scan. That's a scan that you see it in the hospital. So instead of having a person, we put the ice there, and before it melted, we scanned it. And what we've seen is it looks like a tree. So it's even more complex than we thought. It's actually the first crystals that stick there, they tend to grow. And then there are more crystals sticking on the side, and it really forms a tree. And then we took a piece of that, and we cut a thin section of ice, and we put them between 2 Polaroids. And each color here is a single crystal. So you can really see long crystals here. And this ice here, the white, is actually solid ice, whereas this is really like the tree, the anchor ice with the tree pattern. And that's really what you see here. So anyways, thought it was interesting that, people in Quebec really wait a lot before they get the scan in the hospital, but this ice piece really got priority. Then, how complicated can it be in terms of water temperature? I've said water temperature is at 0 degrees Celsius, but here it's actually dropping below. And if we focus on this period, we see this event. We call this a supercooling event. So that's when the water is actually in movement, and it's at 0 degrees Celsius, but it's cooling so fast. Then the temperature of the water actually drops below 0 degrees Celsius, and it starts forming a lot of crystals. That's when the frazzle is really produced. So these peaks there, actually, they're part of the heat budget, and they just make things more complex. If we don't take those into account, we're not able to simulate ice processes very accurately. Then, I think it's the last picture in this section. I took that picture right after Christmas a few years ago, on a river in Quebec, and I was surprised, breakup happened and this was an ice jam. And I thought, well, that's interesting. An ice jam during Christmas, I was not there. I thought there was no rain. I thought it was cold. And then when I looked at all the instruments that we had, I realized that that breakup happened at -25. And what happened here is that the anchor ice that was forming, you remember this little plate that we CAT scanned. Well, that little plate, probably one of the little plates was unstable. And so it moved, and then it tilted, and then it blocked. And then the water level rose, and then the entire ice dam released, and then the following, and then the following. So that breakup actually happened at -25, just to make things more complicated. We think that when it's cold, at least breakup's not happening. Well, guess what? In rapids, it is happening. And that's a rare event, but it can happen. Oh yeah, last picture. I like that one. That's the first picture that I took when I started my doctorate. And my doctorate was about solving river ice processes. And then I thought, okay, so there was an ice jam, and you can see all the shear walls, so all the ice that's on the side that remain on the ice of the river. But then what's this thing? It's like a castle 5 meter high in the middle of the river. And then I had a really hard time to figure how could that remain in place while the ice jam had actually moved downstream, until I realized that it was probably a bigger castle. But then when it started moving, it started to collapse in the water, but then the water level dropped so low that it was standing on this gravel bar, and I could see it on the following summer anyways. So again, really dynamic phenomenal and really complex results. Now, is it easy to do that kind of research? Well, usually, if you're a big institution like the government of Canada, you have instruments, even Yukon government, we have instruments, we anchor them. Sometimes they're flush. Here, that's a research instrument. That's a water level logger in a plastic case on a steel plate with a rebar. So we thought it was robust, but we ended up still losing those at breakup. Okay, so it's really hard to get actually good data, and if we don't have good data, we don't understand. If we don't understand, we cannot simulate. If we don't simulate, we cannot predict. And then people get flooded, and they say, how come you can see it? Well, because my loggers were flushed downstream a few years ago. And also, we keep on instrumenting those rivers, hoping that our instruments won't be flushed downstream. Can we simulate an ice jam? That's a 2D model. Elevation as a function of the main channel distance. And this is the bed of the river. This is the water level here. And all this zone here, it's an ice jam. So you could say, oh, yes, you could simulate an ice jam with an hydrodynamic model. But to be honest, if we want to simulate an exact ice jam, we need to measure a bunch of parameters to make it realistic. So we cannot really predict it. And from a 2D perspective, so this is a town, and this is a river, and the color represents different elevation. Again, very difficult to introduce an ice jam in this, and really difficult to predict where it will jam, how will be the water, how high will be the water level. So we're still not there yet, and that's why we need to do more research on this. Now, Yukon-specific challenges in hydrology in winter. This is a culvert on the Dempster Highway a few weeks ago, and it's full of ice. It's actually half full of ice here, but the upstream side was completely blocked. So the water can get in the culvert, at least when I was there. And so you see a bunch of tubes here and electric wires. That's how Highways and Public Works managed to melt part of the ice just before snow melts. Otherwise, snow would melt. All the culverts would be clogged with ice from freeze up and from winter, and it would just wash out the road at many locations. So this is a real challenge in Yukon. Another challenge, Yukon. I guess everyone's seen that before. Hopefully the fact that we're in the dark doesn't mean that we're at 12.9. I would vote for 4, but anyways. We're definitely in the darker. And what's coming in the future, we know higher air temperatures. We know about the shorter winter, but do we know what's the real impact on breakup, on freeze up and all that on society overall? The answer is, well, partially, but definitely we're lacking some information still, because we still need to understand the dynamics of ice processes and the dynamics of Yukon-specific watersheds. Here's some research done by our team here at Yukon government. Annual minimum river discharge. So that's the discharge at the end of winter. And it's actually green usually means good. Depends who you are. If you're a fish, I guess that you're maybe happy. But you can see a bunch of green dots. So these are hydrometric stations where the late winter flows are actually increasing in the Yukon. So that's an impact of climate change, and it's happening quite quickly here. Another result of climate change is this. So Water Survey Canada, 2010, again, Yukon River. And what you see is, this is, in green, it's the historical maximum discharge, and in blue, it's the historical minimum discharge for an entire year. And what you see here in 2010, is rising. That's the earliest breakup that they've seen in 2010. And then the 2016 was even earlier. So breakup is happening sooner. And what's the impact of breakup happening sooner? If it was only a matter of air temperatures, we could say, well, it's happening sooner, but maybe it's not worse or better. It's just the same. But taking into account the fact that the sun angle is not changing with climate change, the sun angle really affects how ice degrades. So if breakup is happening sooner while the ice is less degraded, we call this more dynamic breakup in the changing climate. So hopefully I'm wrong. Hopefully I've not completed the whole math of that, but my instinct is that maybe we're shifting towards more dynamic breakup in the climate change perspective. You can see here breakup dates. So for the Dawson Lottery, these are all the dates of breakup. So this is the date, 20th of April, 30th of May. And this trend shows that it's decreasing. And right now, I think we are at about May 8th or 7th. Okay, so it shifted. It only reduced by 6 or 7 days over a century. It's not too bad, but maybe it will happen faster in the future. But right now, for the lottery, May 7th. May 7th, and usually midday. Okay, so pick up your hour and minute on May 7th if you believe me anyways. I won't take any part to that. I'm not asking for any ratio. You're win. This was, I've seen that. I was waiting for my plane in Old Crow, and I guess a lot of people often wait for the plane in Old Crow because that's what it is. And it's such a nice place, so it's a good place to wait anyways. And I looked at this, first permanent airstrip in Old Crow. And I thought, wow, that's interesting, look at that. But I believe that the picture was taken because the street was just washed out. The whole river was basically eating the city. And I believe that that's why this picture was actually taken. And then, right now, there's a lot of riprap, rock protection in Old Crow. So I'm not sure, well, they're not sure about the date. Maybe we could look at Water Survey of Canada if they have some data. But definitely, Old Crow is a remote community where breakup and hydrological processes are threatening the life there. This is a picture in Quebec, and I really like this picture in Quebec because this section is about Yukon. So why am I showing this amphibex and this long bow excavator removing an ice jam? in a river in Quebec City last winter. I hope I have the right to show this picture anyways, because I was not allowed to be there, but I was there anyways. And so these houses were flooded by the ice jam, and so the city said, we'll just remove the ice jam. And they hired this guy here, and this guy here, and 3 others, and they just removed the entire ice jam from the city, from the river. It cost like $300,000, I think, in 2 days. And why am I showing this? Because this is not happening in Yukon. If you have an ice jam in Dawson, we don't have the capacity to do that. Or do we? Maybe we should consider it. Anyways. But definitely this is something that is happening south. And is it working? The honest answer is sometimes. But they still spend a lot of money, and people feel good because they see machines in the river, so they think that they will solve their problems. So that's actually a good point. You know, when people feel more comfortable, more confident that decision makers are doing something, well, that's an example. Hydro production in the Yukon, climate change, ice processes. It's really a challenge for Yukon energy. Energy demand is increasing. This is clean energy, but water being spilled, it's definitely not clean energy. It's definitely it's a loss of investment, really. So hopefully Yukon Energy can find a way, and they do that. But hopefully, in a climate change perspective, they can still manage to respect their water license, to manage the flow properly, not affecting fish, not affecting ice, but producing enough energy for people. Hopefully. Yukon News, hopefully was allowed to do that. Anyways, acknowledge Yukon News. This is Dawson. This is the ice bridge. And all the questions, how about the ice bridge, the ice bridge this year? If you log into, if you just log into Dawson camera or something like that in Google, you actually see real-time camera. It's public, it's free. And last time I checked was quite open. And hopefully Highways and Public Works managed to form an ice cover at that location and the ice bridge. But in a climate change perspective, it will become certainly more challenging over time. So now some conclusions, very quickly. Winter is the most fascinating season from an hydrological perspective. I hope you all agree now. Freeze up and break up can be very dynamic. Many dimensions, many parameters, very difficult to monitor, to understand, to simulate, to predict. But you have an apparent chaos, but it makes sense. And if, as a scientist or an engineer, you cannot predict what happened, at least it has to make sense afterward. So that's at least something that we can do. Pretend that it makes sense and find the reasons for that. So our understanding is still limited, and the future is partially predictable. So these are my remarks. And then some thanks. I've used a lot of data from Environment Canada, Water Survey Canada here. My past research team in Quebec City, Laval University, Yukon government, a few data sets from Yukon government here. Acknowledging also my friend Rick. He became a friend in May and passed away also in May. And he was just awesome. He was here for 35 years doing my job. And then big shoes to fill. Yes, it feels like that, big shoes to fill, but it's really challenging. It's really interesting. So that's Rick and Old Crow. And last person to thank is Val and little Adele. Passed away 2 weeks ago. Friends of mine. And if it was not for Rick and Val, I wouldn't be here today. So I thank them for being part of my life, even if it's in the past and in my memories now, but certainly they're with me. So thanks to all. And then, I'll take some questions.
Thank you, Benoit, and consolation and commiserations for all the loss you've had. It's been a rough year.
Yeah.
But yes, we'd like to open this up